Hello viewers, my name is Buba Tamba. Today I'll take you through an experiment to determine the value of g, the acceleration due to gravity. This is so important in our course as physicists. From grade 10 up to any level, you will always come across the value of g, acceleration due to gravity. In most cases, books will tell you take g as 9.8 meters per second squared. They'll ask you to take the value of g as 9.8 meters per second squared, 9.8 meters per second squared, and in some books they will tell you to take g as 10 meters per second squared. Why can we not have just one g, like 9.8 meters per second squared everywhere? In the Gambia, in China, in America, wherever you go, or we just take this one wherever we go. So today, our experiment is actually going to provide answers to this particular question. Now, as you can see on the slide, it says experiment to determine the value of g, the acceleration due to gravity. And what we have is what is called a simple pendulum. The setup that you are seeing on your screens right now is nothing but a simple pendulum. Now, the instructions read, you have been provided with a retard stand, clamp, and boss. A pendulum, in fact, I'll take them one at a time. You have been provided with a retard stand. That is your retard stand. That is your retard stand. Now, this is your clamp and boss. That's the boss here. And this is your clamp, right? Clamp and boss. A pendulum bob. This is where a lot of students have a problem with. This is not called bulb, B-U-L-B, no. It's called bob, B-O-B. B-U-L-B, wrong. It's called B-O-B, right? B-O-B, that is the name of that thing. It's this round sphere that I have here. It's what is called a pendulum bob. And a stopwatch, that is my stopwatch here. That is my stopwatch. A meter rule, this is my meter rule. This is my meter rule. It's graduated in centimeters from 0 centimeters to 100 centimeters, giving us 1 meter. And a string. This is my string. This is my string. A string of length, how many centimeters? 150 centimeters. So I have already pre-measured this, just to save time. I have already pre-measured that. And other necessary apparatus. The necessary apparatus could be the table, the stool that we have used to adjust, and all of that. Now it says set of the experiment as shown in the diagram above. Where is the diagram? This is the diagram. Set of the experiment as shown in the diagram above. Now we will go ahead and set up this apparatus as shown above. Now this is our retard stand. We will attach the clamp, the boss on it, and tight it firmly. Now this is our split cork. In some cases, you are provided with just coins, maybe 2 similar coins. You can use them instead of a cork if you don't have a cork. Now that we have our string of length 150 centimeters, it's important that we measure the length of the pendulum. Now the length of the pendulum, this is very important. The length of the pendulum, suppose you have this as your pendulum, up to here. Let's say this is our rigid support. That's our rigid support. Let's say this is our thread, in some cases a string. And this is our bob, our pendulum bob. Now, what constitutes the length of a pendulum? What constitutes the length of a pendulum is here, the point where the pendulum is actually being supported, toe. Let's call this L. Now, some students would think that the length of a pendulum should come up to here, and they would call this the length of a pendulum. This would not be right, because this does not constitute the length of a pendulum. In some cases, one would decide to bring it up to here to match the length of a pendulum. which would not also be correct. Now, the length of a pendulum actually runs from the point of support to the center of the bulb, here, the center of the bulb. Might not be very accurate, but I hope it makes sense. This is where the length of a pendulum is. And if you are asked to measure 90 centimeters of the 150 that you are given, you are asked to measure from here, from the support to this point, the center of the bulb, should be 90 centimeters. And that is what we are going to do. That is what we are going to do. We would take our string and we would measure the length 90 centimeters. 90 centimeters. That is what we have here. This is 90 centimeters. Here, 90 centimeters, right? If you start from anywhere, if you start from the 0 end, it depends on where you start. It could be at the 90 exactly or at the 10. So it depends on where you start. So this is my 90. Now what I will do is, or what I'll advise all students to do is to take a colored pen and mark that point so that you do not miss the point. And again, since the question would have already been with you, you would have seen that the next slide is asking you to measure 4 other values of L as 80, 70, 60, and 50. I will just go ahead and measure all of them, just for conveniency and to save time. We'll go ahead and measure. I'll measure my 80, and I will mark that. This is my 80, and this is my 70, and this is my 60, and finally 50. You would see why this is important. So now, we are starting with our first length, which is L equals to 90 centimeters. We would insert the string inside the cork. Yeah. I have to confirm that, yes, it's there, the 90 centimeters, exactly. So we tied this firmly. This is done to avoid any shaking during oscillation. So now what we will do is, I'm sorry, the camera would not be able to pick this, and so that is why I have decided to improvise this tool. Now, this table here would now serve as my ground so that you are able to see what we are doing. So that is our L, which is 90 centimeters. The question is asking us to displace small angles of about 1/6 of L. And 1/6 of L is nothing but 1/6 of L is nothing but 1/6 of 90 centimeters, because our L is 90 centimeters. So, and that is going to give us, I think, I should give you about 15 centimeters. I should give you about 15 centimeters, if I'm right. 15 centimeters, right? So, since we do not have, the reason why we are doing this is because we don't have a protractor that we can place here right now and do that measurement. So we would use this, the meter rule. We would go to where the pendulum, the bulb points directly on the ground. We will mark that point. We will mark that point, and then we will measure 15 degrees, 15 centimeters, either right or left. So, 15 centimeters from the point where the bulb directly points on the ground. This is where the bulb points on the ground, directly, vertically downwards. So we would mark that point, And then we will measure 15 centimeters to the right and to the left. So this is our 15 centimeters. From 0 to 15, that's 15 centimeters. 15 to 30 is another 15 centimeters. Now, this is important because when we displace it beyond this angle, what happens is it does not obey the law of physics. Now, this is what we call isochronism. Isochronism. So what we need to do, basically, if we do not obey these 15 centimeters, then that means we are not obeying a principle in physics, because the period of a pendulum is given as 2 pi, the root of L over G. And if we go beyond these 15 centimeters, then the physics is disobeyed. This equation will not hold. So that is why the instructions will always clearly tell you that you displace through small angles. And please don't disobey that. Now that we are ready to displace our pendulum, we must have our stopwatch ready. And they must be set to 0. The question says, displace the bulb for a small angle, 1/6 of L. L is 90 centimeters. Read and record the time T that it takes to make 10 complete oscillations. And an oscillation is basically the to and fro movement of an object in space. That is what an oscillation is. So when the object moves and it comes, it makes 360 degrees. If it is going only, if it goes only, that's 180 degrees. And if it comes again, it's 180 degrees. Now, students will have a problem. Most students have a problem determining what actually constitutes an oscillation. That is what I have just explained. Now that we have our stopwatch ready and we have our setup also ready, we go ahead and begin to oscillate. Now, we will oscillate obeying the principle, the 15 centimeters, that small angle displacement. And now we are going to displace and we will begin taking our timing. Here too, there is a point to be noted. Now, it's going to be very difficult for you, because of impulse issues, it's going to be very difficult for anybody to accurately, because we are not machines, but we do our best to make sure we are in line with the principles of physics. So we do not give it a push, because if we give it a push, then that means we have given it an extra energy. We just have to allow it to oscillate freely. So what we do is we displace it through small angles and you leave it. When you leave it, it will oscillate just by itself. And then you can begin to take your timing. Now here, if I want, I can begin my stopwatch. I'll just punch my stopwatch by the time it comes here, and then if it goes and comes again, that is one oscillation. If it goes and comes again, it's another oscillation, which is 2. If it goes and comes, it's another oscillation, which is 3. And we must also avoid what is called conical oscillation. Conical oscillation is basically when you see, it's making a circle. That is what is called conical oscillation. All of this will have to affect the time. Why? Because now let's say you are on a race, and this is the start point. This is the finish line. Now you are point 1 here, athlete 1 and athlete 2. Now athlete 1 goes straight to the finish line, and athlete 2 is making a curve. Who will actually get to the finish line before the other? Obviously, it will be athlete 1. And this is actually taking your time, which will also have a problem with this. It will not obey. Also, we must avoid what is called dangling. Like if you pull it too hard, what happens is it dances. And as it is dancing, it's the same. Now let's say somebody is running, athlete 1 still, continuing on that straight path, and you are just jumping. You are going, but you are jumping. Who will get to the finish line before the other? Obviously, athlete 1 would get to the finish line. So all these are points that we note as we do this experiment. So I hope you all know this too. So we displace it through small angles. We allow it to go. And now we can take our reading. I will punch my stopwatch now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll stop my stopwatch now. What I have is 19.00. 19.00. That is what I have. So don't stress yourself with the points that you have. A lot of students would always stress themselves with these points. Just make sure you do not disobey the laws of physics. If you do not disobey the laws of physics, you are always going to be safe. Now I will do this. I'll preempt this question because I know at some point it will ask you to draw a table, so I'll quickly do that. These values, these boxes are all important. These boxes are all important. Now the first one here is actually going to be our L, and our L is measured in centimeters. This is important. Why? At this point, when you label your unit inside the box, then you can easily, comfortably just write the numbers without having to write the units beside them. But if you do not do this, if you do not place their units, then you will have to write their units beside them like that, all across. All across. And this is going to take your time. So what we advise students to do is to simply write L and you put centimeters around it, just beside it, sorry. And we have 90, 80, 70, we will have 60, and the last value is, of course, 50. Now, the question is asking you, in each case, it says determine the value of t, the time it takes to make 10 complete oscillations. How do you get the time it takes to make 10 complete oscillations? So t is going to be in seconds, and usually what we advise students is to take 2 t's and then take the average of that. They will take the values of 2 t's, so therefore I'll call this one t1, and I'll call this t2. It's also going to be in seconds. Time is always in seconds. And then we will take the average of that. Now the average of that is nothing but t1 plus t2 divided by 2. Also is going to be in seconds. Now after you have done that, you determine the mean value of the time, the mean t, which is nothing but t, because this is going to be now the t average. Even though I did not write t average, we can write it somewhere. You can write it t average, which is equal to that. So now we can call this t average is equals to now t mean, the mean value of t, which is time, the actual time, is equals to t average divided by the number of oscillations, the number of times that you are asked to oscillate it, which is actually the period. And in our case, it's nothing but 10, right? And also, you will take t squared. Now here, students have a problem. Again, before I go further, I need to indicate the unit of these two. This is also going to be in seconds. And the last column that we are going to have will now be t squared. This will now be t squared. And t squared is nothing but whatever value that you have here is what you are going to square. Now the problem with some students here too, they will just see t and they will write seconds. T squared, they will write seconds, which is going to be wrong. It's going to contradict your work. So t squared, obviously the unit will also be t seconds squared. Now this is what we have. Now after we have done our first oscillation, what value of t1 did we have? We had 19.00. Also the units, the decimal points here, they matter a lot. If you are keeping to 1 decimal place, you must maintain 1 decimal place across the experiment. If you are keeping to 2 decimal places, you must maintain that too across the time of the experiment, right? So now let's go ahead and do our second value for t. T2. You will reset you must make sure you reset your stopwatch. Now that we have reset our stopwatch, we will do another one. I will wait until when it comes here, and then I'll punch my stopwatch, right? All of you. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I got 18.93. 18.93. I got 18.93. 18.93. So what we are now going to do is we are going to adjust. You know, we have already done for 90, right? And if we are to add this up, can I have a calculator? Where is my calculator? Okay, let's just add this up. What is going to be 19.00 plus 18.93? Okay, so now that we have our second value for t, which is 18.93, we will just go ahead and add these two and take their average. So 18, sorry, it should be 19 first. It's either way, it's cumulative though. 19.00 plus 18.93. We will have 37.93, and we will divide that by 2 because we are taking the average. We are taking the average, remember? We are taking the average, and we'll have 18.97. If we take the average here, now it becomes 18.97. Now that we have taken that average, what we are going to do is to divide that average to get the period of oscillation. The period basically is the time it takes for a pendulum to conduct one cycle. So if a pendulum is released from here, if it goes, that's 180 degrees. If it comes, it's another 180 degrees. So that is what is called a period. If it goes like this, 180 degrees going and coming 180 degrees. So that is what is called a period. So we want to know for our case where L equals to 90 centimeters, what was the time it took for this pendulum to conduct just a single oscillation, just one. And that is going to be, we simply divide this by 10, because whatever we get here, we divide it by 10. And that is going to give us 1.897. So this is the period. Now what this is telling us is that it took this particular pendulum, when the length was at 90 centimeters, it took it about 1.897 seconds to conduct just a single oscillation. That is a period. Going and coming, just one. That is one cycle. It took it 1.897 seconds to conduct a complete cycle. That is to go and come, which is 360 degrees. So now we are going to square this. This is important for some reason, and you will come to see pretty much soon. Now when we square this, we have 3.599. 3.599. Now, we are done with the first value of L, which is 90 centimeters. Now we are going to move to the second value of L. And that was the reason why I had decided to mark all the values. Because this is 90 now, this value here is 10. If you remove 10 from 90, you are left with 80, which is actually corresponding to what we have on the board. And if you remove 20 from 90, you are left with 70. If you remove 30, you are left with 60. If you remove 50, if you remove 40, you are left with 50. So that would constitute the length of the pendulum. Now let's go ahead. I'll have to bring this down somehow. I'm sorry. And then we will adjust this. Adjust it to 80. And this is what we advise students to do. Because if you want to remove everything, the string, and you want to measure again, that is going to take your time. And you don't really have time. During exams, you are under tension, and You have to manage your time really, really well. So now that we have this, which is 80, we are going to take 1/6 of 80 also, so that we are within the guidance. This is what will always guide us, 1/6 of 80, to give us how much do we need to displace it. Now 1/6 of 80 is nothing but, that's 13.33. So we have 13.33. So it can be, the displacement can be less than this, it's not a problem, you are still within the principle. But if it is beyond this, you may have disobeyed one or two things in physics. So we'll have to reset our watch to 0. You'll have to reset this watch to 0. And then we would now begin to displace. We would displace through small angles. We have to measure the 13.33. This is where it is vertically down. Here, we mark that point. Be careful, if the points are too many, there could come some confusion. So this is 10. This is 13.33. So we'll measure this point here, 13.33, and we'll measure this side to 13.33. So we'll make sure the displacement is within this, right? And we will begin now. Make sure the stopwatch is set to 0 before you begin. Now we would allow it to oscillate. No, this is not the best. So I'll count once it comes to me here. That is when I am going to punch my stopwatch and then begin the counting. I'll count after the count of 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. That is what I have. Now at 10, I have 18.09. 18.09. 18.09. So at 80, what we have is 18.09. So we go ahead and do for the second value, because that is just T1. That is just T1. Now we are going to do for T2, and we are going to release. No, this is conical oscillation. That's why we must always allow it to freely come to rest, and then you just displace it. Okay. After the count of 3, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 17.94. 17.94. Now that we have 17.94, we will take the average. Now we will take the average of that. Now the average of that would be 18.09 plus 17.94. 36.03. We divide that by 2, we'll get 18.02. 18.02. Now this 18.02, if we divide it by 10, we get 1.802. Now we will take the square of that. We'll take the square of that, and what we get is 3.245. 3.245. I hope you are seeing the pattern now. So now we will go to 70, and at 70 we will just do like we did with 80. We will remove it and adjust it quick. We'll bring it down, adjust it to 70. It would adjust it to 70. It's 70 here, and we will tie that too, and we will place it back. I need my stopwatch. I'll reset the stopwatch to 0. And now I'm going to displace it. Now for 70, you only have to displace within 11.7 centimeters, following the previous method that we did. So we're going to displace that too, right? If we displace this, we allow it, and then we can take our timing. We begin 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 16.84. 16.84. Let's do a second one to take to have the second value for t. Oh, it's not correct. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 17.03. 17.03. So now we will just quickly do all quickly, and then we would go to the board and perhaps permanently be on the board. We now go to 60. If you take 1/6 of 60, you have 10. You have 10. If you take 1/6 of 60, you have 10. So what we will do is, what's my stopwatch? Yeah. Thank you. So I have to reset my stopwatch to 0. And now I'll begin my displacement. Excuse me, I'll have to take this again. Okay. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15.53. At 60, we have 15.53. We will do again the same value, or the same value of L. We will do again. Displace through small angles. I'm not satisfied with that. Okay, good. Excuse me. I'll begin my stopwatch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15.72. 15.72. And the last value, which is 50. We'll bring it down again. We adjust to 50. We'll adjust to 50. Remember, the mark is already there. And then we will take it up again. Take it up again. And 1/6 of 50 should be around 8.3. So note that. So we are within that in terms of displacement. No, not satisfied. I'll take that again. Where's my stopwatch? No. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.31. So we have 14.31. We will repeat for T2. We would repeat for T2, and then we would be done with the, no, this is dancing. Okay, great. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.22. We have 14.22. So this is what we have. Now we would do the averaging and fill the table. Now the first thing that we are going to add is going to be 16.84 plus 16.84 plus 17.02, 17.002, 33.86. We divide that by 2, and we'll get 16.93. 16.93. Now, if you divide that 2 by 10, you get 1.693. And if you take the square of that, we get 2.866. 2.866. The same thing is going to be done with this case, 15.53. 15.53 plus 15.72. We'll divide that by 2. We'll get 15.63. And if we divide that by 10, we get 1.563. Now, if you take the square of that, 1.563 squared, we get 2.443. This is what we get. And finally, we have 14.31 plus 14.22. We'll divide that by 2, and we get 14.26. We'll divide that 2 by 10, and we get 1.426. If we take the square of 1.426, what do we get? We get 2.033. 2.033. So this is what we have as far as this experiment is concerned. Tabulate your readings. This is what it means to tabulate your readings. So during examination, if you follow the instructions, in fact, tabulating your readings alone gives you marks. I think it's about 2 points. The table alone gives you 2 points, the table alone. So that's why you must always tabulate your work. Tabulate your readings, always. So the next thing says, plot a graph of t squared on the vertical axis against L on the horizontal axis. Plot a graph of t squared on the vertical axis. Now, if you have your graph like this, this is now going to be your t squared against L on the horizontal axis. L is going to be here. So now what students normally do is they will just put t squared on the vertical axis and put L on the horizontal axis, and they will forget the rest, right? Which is not really okay. So when you level your axis, you write t squared, you put in bracket seconds squared, right? L, you put in bracket centimeters, right? And then you go ahead and plot your graph, right? So, now when you look at these values here, if you are a very smart student, what I normally advise students to do is, because students find it very difficult to work with decimals, now I advise them to convert these values of t squared into whole numbers. How do you convert this? It's simple. You look at these values here. You know you can easily make this one. You know here, you can easily convert this to give you 4. You see here, gives you 4. The next value that comes after what you are looking at, after the whole number. Look at the first value, the first decimal that comes after the whole number, the first decimal. If it is 5 or below, if it is 5 and above, you can add the whole number and you can increase the whole number and make it, you can increase it by a unit. If it is less than 5, then you cannot. You just drop it and just take the whole number that you have. So this one we can make it 4, and this one we make it 3 because this is 2, and this one too we make it 3, this one too we make it 2, and this one here too we make it 2. Now when you look at this, you have 2, 2, 3, 3, and 4. So basically these 3 points can actually give you a graph. If you are able to have all of these points accurately done, like if you have 2, 3, 4, 5, and 6, then that's fine. But then this is the result of our experiment because it cannot be perfect. You remember we have impulse as the time when we are releasing the bulb. You know, there could be some problems that actually affected the period of oscillation. This is actually as a result of the period of oscillation being affected by one thing or the other. You understand? So after we have obtained all of these values, now these values is what we are going to take and plot against L. This is what we are going to take and plot against L, these values that we have here. And now you have a whole number. These are whole numbers that you are going to take and you are going to plot them against whole numbers. Now I have taken you off the trouble of plotting decimals against whole numbers. It's really fine. You can also work with this. That's why I decided to leave this here. You can work with this if you are okay. If you are not okay, you just change them to whole numbers and then you draw your graph. Now we will go ahead and draw our graph quickly. Now that we have drawn our graph, I'll go to the board to show you how this is also done. So you can have your graph like this. I'll quickly show you this. Right? So now the question is asking you to, after you have plotted your graph, plot a graph of t squared on the vertical axis against L on the horizontal axis. Determine the slope of your graph. Now the slope of your graph, even if you, like what some smart students will do, after they have plotted their graph, they will just go back to their tables and then they would get their values and quickly do their slopes, which is really not advisable. It's not advisable. But if you go according to your graph, if you go back to your graph, you can easily find your slope. For example, the slope is basically the gradient of graph. Now what we will do is we will plot our points. Now our first point, 90, corresponded to 3.6. Now 90 actually was here, L is 90. This is t squared. We better label that too. T squared in seconds squared. Now 90 actually corresponded to 3.6. Now this is 3.5 here. This is 3.5 here. And in between 3.5 and 4, you have 0.5. 0.5. If you don't know how to do this, you better take your calculator and point. Now 0.5, 3.6 should be somewhere around here. It's not very far from 3.5, 3.6. So you take your calculator. This is not actually drawn to scale. It's not actually drawn to scale. But then we would draw a line that comes from somewhere, from here. Not necessarily draw a line, but something that guides us that far. And then we would take our 90 and make a point, or mark a point. It seems that's the very point here. That would be our 90, right? And the next value is 80 corresponded to 3.2. 80 corresponded to 3.2. Now this is our 80 here. Our 80 is here, and it corresponded to 3.2. Now 3.2 should be somewhere here, not very far from the middle of the midway between 3.0 and 3.5. So the midway should be around 3.25 or so. So 3.2 should be around here. On your graph sheets, you should be able to do this without any problems because it's already drawn to scale. So what we are doing is we're marking a point here. And the next value, 2.9 corresponded to 70, or 70 corresponded to 2.9. Where is our 70? This is our 70 here. 70 is here, and 2.9. Excuse me. 70 and 2.9. 2.9 is very close to 3, somewhere around here. It's very close to 3. So and then 60 and 2.4. 60 and 2.4. 60 is here. 60 and 2.4. Around here. 60 and 2.4. Somewhere here. And finally, 2.0 and 50, which is just easy. 50 is here. 50 is here. And 2.0, we'll still have to do the marking. And 2.0 there. So we have another point here. So now that we have done all of this, we go ahead and draw our graph. We will now go ahead and draw our graph. Now if you look at these points, there are points that are actually off the graph, and there are points that are actually on the graph. It seems that these points are on the graph, like this here. These are the points on the graph. This is 50, 2.0 and 90, 3.6, 90, 3.6. Usually the x comes before the y. So now we find our slope. The slope S is given as the gradient in y and that of x. That is to say, normally we have a famous way of doing it. We'll call this y2 minus y1 all over x2 minus x1. Now if you look at this, we would suppose this to be our y2 here, and we would suppose this to be our y2, and this is x2 or x1, it does not matter really. This one would now be our x1, and this would be our our y1. You can work it that way. So now if we take y2 as 3.6 minus, what is y1? y1 is 2.0. Divide that by x2, which is 90, minus x1 is What is x1 is 50. So we get 6, 1 all over, I hope 40, yes, 40. So if you take your calculator and you punch, what are you punching? You're punching 1.6 divided by 40. You get 0.04. You get 0.04. 0.04, but now remember, you're plotting t squared, which is now going to be second squared per L is measured in centimeters. In centimeters. Right? So what you need to do is to basically convert this to meters. And if you convert this to meters, what you get is, you just multiply it by 100. What you get is 4 seconds squared per meter. This is what you should get as your slope. So if you have done this properly, it does not matter what value you took. Even if you decide to take the first value and the second value, where was it? And this one here, make sure the values that you are taking for your slope are values that actually are on the graph. They cannot be values that are off the graph. If they are values that are off the graph, then you will have problems, because values that are off the graph are the ones that really had a problem during the course of the experiment. So now that we have our slope, we can label this as A and we label this as B, just to denote the points that actually gave us our gradient. So now that we are able to determine our gradient, now to determine the value of g, the acceleration due to gravity at this particular point where we conducted the experiment, we know that t is, that is the period of oscillation of a simple pendulum, is given as the root of, 2 pi, the root of L over g. Now we just want to make g the subject of the formula. All we need to do is to just square all sides. And if we square all sides, what that gives us is distance as t squared is equals to 4 pi squared L over g. Now that we have this equation, right, we can simply, to determine the value of g at this very location, we can simply take g to be equals to 4 pi squared L over t squared, right? Now at this point, we'll take 4 pi squared, and L, we can go back to our equation. We can take whatever value that we take for L, we take the corresponding value for T. So let's say L is 90. Let's take 90, all that over. 90, what was the corresponding value? I think it was 3.6 or so. We'll take 3.6, right, for T squared. And if we point this, let's see what we get. 4 pi squared times 90 divided by 3.6. We get 986.960. So this is the value that we have for G. But remember that this is, what is this? L is in centimeters. So the unit is going to be in centimeters per seconds squared. So to standardize this, what we need to do is just to divide it by 100, and then we would have 9.86960 meters per seconds squared. This would have been the value of G at this very location where we conducted this experiment. So this is why the value of G is not just a unique constant such that it remains this everywhere you go on the surface of the earth. It depends on your altitude or your location as far as the equator is concerned. So this is why we have, here you have it as this. If you go elsewhere, you may have it different, slightly different from this. Slightly different from this. And other places, that's why some books will give you 10.0 meters per second squared. So this would now be the value of G at this very location. The location is basically the science lab at Canifing. So that brings us to the end of today's lesson. I hope to see you in our subsequent videos.